Finally, let's talk about one last mathematical concept, infinity. We're kind of breaking the rules here, as infinity isn't technically a number, but it's still relevant to the numbers we've looked at today. Infinity doesn't act like regular everyday numbers, because it isn't a number at all. You can get an understanding of the strangeness of infinity by staying a night at Hilbert's Infinite Hotel. Imagine this: you're the manager of a hotel with an infinite number of rooms. On one particular night, the hotel is completely full with a guest in each of the infinitely many rooms. A new guest walks through the doors, asking for a place to stay. If this was a finite hotel, you'd have no choice but to turn them away. But this is an infinite hotel, and that's special because you can move each person to a room one up from the one they're staying in. The person in room 1 moves to room 2, the person in room 2 to room 3 to room 4, and so on. With this nifty trick, you can accommodate any number of new guests by moving the guests in room n to room n plus a, where a is the number of new guests. Sure, those already in the hotel won't be happy about it, but it works. This is all lovely, but now suppose that an infinite bus containing an infinite amount of new guests shows up, and they all want to stay at your hotel. What do? Well, luckily, the hotel is equipped with a manual on how to deal with these kind of situations. In this manual, you find the solution. You tell your guests to move to the room with double their room number, leaving only the odd numbered rooms available to the infinite hordes of new people. Now let's take a look at one final scenario. Look out the windows of your infinite hotel and see an infinite number of infinite buses on the driveway. In other words, infinity times infinity, or infinity squared amount of people hoping to have rooms. Is it possible to give them all rooms, or will you have to turn them away? Luckily you won't have to, and here's how to accommodate them. Number everyone in the infinite bus from 1 to infinity, and then have all the infinite buses also numbered 1 to infinity. Now create a grid with the buses from 1 to infinity in the rows, and the passengers also in the rows. We can turn this grid with infinite area into one single infinite line by doing this. We can start out with the first person on the first bus, or 1-1, then go to 1-2, and then 2-1, and then 3-1, and 2-2, and so on. With this new infinite list, we can do exactly the same thing we did with the single infinite bus, and put all the passengers of the infinite buses into the odd numbered rooms. We can write all these scenarios in equations as such. Infinity plus 1 equals infinity. Infinity plus infinity equals infinity. And infinity times infinity equals infinity. The last two equations can be used to show some pretty interesting results. The infinity of the even numbers is the same as the infinity of all the whole numbers, which can be shown by taking the even numbers and matching them 1 to 1 with the whole numbers. The infinity of the positive and negative whole numbers is the same as the infinity of just the positive whole numbers. The infinity of the fractions can also be shown to be the same as the infinity of the whole numbers. We can do this by creating a grid, similar to the infinite number of infinite buses example, and doing everything the same, apart from this time we'll skip out fractions we've already seen. The winding snake-like structure created can then be unravelled into a singular line, and the fractions matched up with each of the whole numbers. From this, you may assume that all infinite amounts are the same, and that Hilbert's Hotel can accommodate any number of guests. However, this isn't true at all. Gale Cantor showed that there wasn't just one kind of infinity, but an infinite number of infinities. Some infinities are bigger than other infinities. The infinity we've been dealing with is the smallest infinity, the infinity of the counting numbers. Cantor described this as countable infinity and used the symbol aleph null to represent it. To find bigger infinities, we need look no further than the real numbers. Can we match up the real numbers with the whole numbers? Cantor showed that you couldn't with a technique called Cantor's diagonal proof. This asks you to imagine that you created a list of all the real numbers and then shows you that you actually haven't. Here we have our list of reals. We can create a new number by circling the first digit of the first number, the second digit of the second number, the third of the third, and so on. We'll then add 1 to each digit, going back to 0 if it's a 9. Using this method, we've created an entirely new number that is nowhere to be found in the list, as each decimal place is different from each of those in the list. Even if we add this number to our list, we can do the whole thing again and create an entirely new number. This list is incomplete, and therefore the infinity of the real numbers is bigger than the infinity of the whole numbers. To get an idea of just how tiny countable infinity is to the uncountable infinity of the reals, if you were to throw an infinitely thin dart onto the number line, the chances of you hitting a rational number are quite literally 0%. The numbers we're familiar with are nothing compared to most of the numbers out there. The infinity of the constructible numbers is countably infinite, whereas the infinity of the unconstructible numbers is uncountably infinite. In addition, the infinity of algebraic numbers is countably infinite compared to the uncountable infinity of the transcendental numbers. The infinity of the reals is the same as the number of points on a line and the number of points on a two-dimensional surface. To get an even bigger infinity, consider a flat plane. Now picture all the possible combinations of lines, curves and squiggles that could be placed on this flat plane. The infinity of all of this is a bigger infinity than the infinity of the reals, and is the highest infinity used to measure an actual amount of something. Another way Cantor created infinities bigger than Aleph Null is through the concept of power sets. The power set of a set is simply the set of all subsets that can be made from a given set. The number of subsets in a power set is simply 2 raised to the power of the number of members in your original set. So a set of 4 objects can be used to make 16 sets. The power set of all the counting numbers is a bigger infinity than Aleph Null. We can do Cantor's diagonal proof again to show this. Create a list of 1 to infinity and try to make a list of all possible subsets by putting a 1 to denote a number is in a set and a 0 to show that it isn't. And now create a new set that isn't in this list by doing the same thing with the real number proof, but instead turning 0s into 1s and 1s into 0s. And lo and behold, we can create a new set that is nowhere to be found within our list. The function of power set in infinite sets can be repeated continuously, creating bigger and bigger infinities. Cantor's idea about infinity was so radical at the time that many of his contemporaries openly mocked him. Henri Poincaré described Cantor's work as a malady, a perverse illness from which mathematics would be cured. Leopoldo Kronecker, Cantor's former teacher, called him a charlatan and a corrupter of use, a phrase you don't typically associate with mathematicians. All of this resulted in Cantor experiencing a nervous breakdown at the age of 39, followed by a lifetime of mental health problems and hospitalizations. While his ideas never saw recognition within his own lifetime, they are now universally accepted by mathematicians. Cantor wondered whether the infinity of the real numbers was the next largest infinity from the infinity of the whole numbers, or whether there were infinities between the two. This is known as the continuum hypothesis. Cantor believed that there probably wasn't, but didn't know for sure. To this day, the answer to this question is still unknown. Not only is it not known, but it's actually impossible to know. Not because we don't have the mathematical knowledge to do so, but because the question itself is unanswerable. The discovery that some mathematical problems are unprovable is referred to as Gödel's incompleteness theorem. So while mathematics may seem like the ultimate form of logic and truth-seeking about the universe, it still has its limits, and there are things out there in the mathematical landscape that we will never know the answer to, and can never know the answer to. Thanks for watching.